So last but not least this week, we've been talking about transformations a lot all week, kind of what they are, how they work, and how we go about coming up with the matrices that define these transformations, and really thinking about AX equals B as not only a system of equations or vector equations or a matrix equation, but now we're thinking about it also as a transformation, where the matrix A, is a transformation from one space to another. We pop in a vector X, get out a vector B. And one thing that it turns out that we're very interested in is whether or not these transformations are what we call one-to-one or onto. If you've taken pre-calculus before, you may have covered these topics as they refer to functions. And the idea behind them is exactly the same. So the purpose of this is, it turns out that we need one-to-one and onto these properties of a transformation being one-to-one and onto in order for the inverse of a transformation to exist, just like the inverse of a function exists in pre-calculus or algebra and good old-fashioned math that we used to do before. So we're going to talk about these two, and actually we're going to start with one-to-one here. So we're going to do a definition. So as a definition, okay, a transformation or a mapping. So I'm going to just mix in the lingo a bit. A transformation or a mapping T that goes from Rn to Rm is said to be one-to-one. Is said to be one-to-one, or what we call sometimes or injective is the very fancy term, injective. So a mapping is an injection, or it's injective if for all vectors B in Rm, they are the image of, at most, one vector X that we're getting from Rn. Okay, so another way to think about that is, if we consider the matrix equation that represents a transformation AX equals B, oops, no parentheses yet, then this either has a unique solution, X, or no solution for any vector B that we pick from. So for any vector B that's from Rm. That's one way to think about it. So these technical definitions are pretty hard to work with, so I'm going to, of course, draw a picture. So let's pretend that we're hanging out over here, and this is going to be our domain. So our domain, in this example, our domain here is Rn. And so we're going to have some vectors in here. We're going to have like some x vectors. So these are all different vectors, so maybe I'll call them the x1 vector and the x2 vector and the x3 vector, etc. And then we also have a range, or excuse me, a codomain. Sorry, not range technically. So we have a codomain. So the codomain is where all of our outputs live. Remember, the range could be smaller. But the codomain here is going to be Rm. And ideally, we have some B vectors. So B1 here, B2 here, and B3. And remember the transformation T, right? T is taking a vector from here and mapping it to something over there. And so what it means just visually, right? If we have this transformation T, what's going on here is if we're one-to-one, that means that that if I consider all of these little x1, x2s, x3s, let's say, I could say, that x2 goes to that vector b1. I could say this vector here goes to b2, and then x1 goes to b3, and this is a one-to-one relationship. Okay, so you can see that according to the definition, each of these b1s comes from a vector x in our domain, and specifically, they don't come from more than one. So for instance, if for some reason this split, and let's say that that x2 mapped to b1, but then x3 also mapped to b1, this is a problem. And the reason why this is a problem, because if in the future we want to go backwards, right? We want to do an inverse and we want to start here, and I ask you, okay, what vector x did you come from? You wouldn't be able to give me the answer because it's being split amongst two different vectors over here. So in this particular case, this right here, as I've drawn it, is not one-to-one. So for one-to-one, we need this to happen. Now, one thing worth mentioning is that when we're talking about one-to-one, we're going to assume that in our domain here, that all of these x values belong in our domain. So a very common question a student might ask is, hey, if I just do this, is this transformation one-to-one? And I would say, well, if you want to ask that question, you have three different x vectors here that live in the domain, but you're only considering one of them, which doesn't make any sense. The idea is that the domain is representative of all of the input vectors that work in this transformation. So when we talk about doing a mapping from Rn to Rm, we are assuming that all of these x1, x2s, and x3s get assigned somewhere. So it is totally fine to have like an extra b4 vector here, and I could have maybe this vector goes here, and then this vector goes here, and we don't have anything assigned to b4. That's okay, because the range of our transformation would be those guys right there. The range of our transformation would be b1, b2, b3, and it's okay that there's more vectors outside of that in our codomain that are not part of our transformation, which kind of makes sense. Like if this is R2 and we're mapping to a much larger R3, odds are there's probably going to be leftover vectors. So the only thing that we care about when we're talking about one-to-one is just if we start mapping things, do all of these B vectors come from at least one, or exactly one, or none of those input x1, x2, x3 vectors. Okay. A next natural question that people ask is, well, can I have something like this? Is this still one-to-one then? Right? If I have this, let's say let's put my B4 back into here. And so I map this one to B4 and this one here. Now, does this satisfy the rule? And I'd say, well, this is not a valid transformation, and you can think about why is like it's not valid because just like functions, a function maps one input to one output, and we fail being a function because this x2 right here maps to two different vectors. So this doesn't even classify as a transformation as we know it, because we get one input in and one input out. So we don't concern ourselves with that case. We just concern ourselves with if we're one-to-one, then each of these B1s, have some input vector that they've come from, or none, right? But this would not be one-to-one if I were to draw it like that. This would be one-to-one like so. So arithmetically, what does this mean? This means that if we're considering a linear transformation and we're thinking about it in this particular form right here, ax equals b, what we're looking for when we're talking about one-to-one is the same thing as asking, does this matrix equation have a unique solution for every b, every b that exists in Rm. That's what we're wondering. So by unique solution, what we mean is, look, either either there is no solution, right? Or there exists some x in some x from Rn such that x, this vector x, is unique. So this is a very shorthand notation of writing this. But basically that whatever solution that it is that we come up with, whatever vector x that we're finding here, has to be unique. So they can't, there can't be an x over here that is shared with another vector b. We can't get the same one anywhere else. It has to be unique. Okay, so now we're gonna kind of mosey onwards to onto. So definition, right? What's the other classification of a transformation? So the other transformation is, or the other definition is that a mapping T from Rn to Rm is said to be onto, we call onto, or what we call surjective. Onto or surjective if for all vectors b from our codomain Rm, let's make that actually an m, from Rm, that every single one of those b's is the image of at least one vector x in Rn, our domain. Okay, so this is another way of saying, so I'll write this down. So this is another way of saying, that the range of T and codomain of T are the exact same. And so let's draw a picture, because that's a lot to internalize right there. So here we have our domain Rn, and we have our transformation T taking us from one place to the other. We have our codomain Rm, and in here lives some b1, some vector b2, some vector b3, etc. And over here live some x's, so x1 vector, x2 vector, x3 vector, etc. So in order to be onto, what this basically says is that none of these b1, b2, b3 vectors are just existing on their own. Basically that they have to have come from they have to be mapped to some vector in Rn. Now again, this exactly wouldn't make perfect sense, but I'm just going to write it for illustrative purposes. Notice that we're not one-to-one. So we're not concerned that each of these B1 and B3s are coming from a unique X2. We just care that we could come up with every single output vector that's in our codomain, right? That every single one of these comes from Rn, our domain. And the reason why this statement that says the codomain and the range are the same is because what being onto says that every single vector in this space came from somewhere. That's what it's saying. And so if that's the case, then the range of our transformation is all of those values, but all of those values make up our codomain, so we don't have any small subsets. Our codomain and the range are the exact same. Okay, so maybe I'll modify these pictures a little bit. So let's say, so an example of something that's not onto would be something where we have a mapping here, a mapping here, and then we have a mapping here. So is this one-to-one? I believe so. It says every single, oh no, actually it's not, right? Because this is not one-to-one, because by definition, every single one of these vectors here has to come from either have no solution, or it has to come from at most one previous vector. So as I've drawn it, this is not one-to-one. And it's not onto because that little guy right there doesn't have anybody that it came from. So that is an example of maybe a sort of visual aid of where we wouldn't have one-to-one or onto. Let's add a fourth vector here and see if we can figure this one out. So if x1 maps to b1 and x2 maps to b2 and x3 maps to b3 and x3 also maps to b4, while this is not one-to-one, it fails one-to-one. Actually, it's not that it fails one-to-one, it fails to be a function, right? Because each of these b1, b2, b3s, b4s, they come from at most one x value, right? Even here, each of those come from at most one input x value. So it kind of looks like one-to-one. And then the fact that all of these are associated with an x value basically means that it is also onto, but we fail being a transformation because this little guy, just like we would if we failed to be a function, maps to two separate x value, or excuse me, maps to two separate output values, so that doesn't work there. And so the most ideal situation of what we would have, the most ideal situation is that we have just a nice perfect mapping of something like this, where we satisfy one-to-one, because for one-to-one, the definition is that each one of these vectors, b1, b2, b3, is the image of at most one vector in Rn, in our domain. And that's the case. b1 is the image of x1. b2 is the image of x2, and b3 is the image of x3. Great. That satisfies the at most category. Is it onto? Absolutely, because the definition of onto is much more simple. It's just that all of these vectors here, b1, b2, b3, are associated with some vector x1, x2, x3 over here. Okay, so how does this relate to, again, the matrix equation that we've been working with before? Well, the matrix equation AX equals B comes into play here because asking whether or not a transformation is onto has to do with whether or not, we're asking the question, does AX equal B have a solution? Have a solution for all B in our codomain Rm, right? Does this happen? If this is the case, if for every single output vector B that lives in our codomain, it comes from some input vector, aka we can always solve this, we're good to go. And remember that, doesn't necessarily mean that this is, if I erase all of these, that definition, and there's just like an x1 vector, I could create mapping like this, something like this, and it looks absolutely ridiculous, but on the outwards appearance, this is onto because all of these B1s, B2s, B3s they have something that they came from. Okay, that's the idea. The point of adding the one-to-one business ensures that we get a unique relationship that it's, not only does it come from somewhere, but it comes from at most one value. And that's kind of important because once you have that, we have our x2, x3. If we have these criteria working together, we can create a bridge, a perfect bridge from one space to the other, where I can kind of walk back and forth. I can think about, not only does my transformation go this way, but I could think about having an inverse transformation that takes me back the other way as well, which we're not going to talk about yet, but that's kind of somewhere where we're going. Okay, so that was a lot of information. I'm going to cover a couple theorems, maybe do one example, and we will call it a week. So here we go. A theorem. Okay, so let's let T go from Rn and map to Rm. And we want this to be a linear transformation. So let T be a linear transformation. That's going to be a very common theme throughout this class. It's called linear algebra. And we're going to let A be what we call the standard matrix for T. So the standard matrix for T. Standard matrix for T, this is just fancy notation for the fact that we're using, that basically we're defining T of X to be equal to AX. So we call A the standard matrix for T. So we have a linear transformation, we have some matrix. And I'm going to list two little kind of fun details that we get. All right, so number one. So T maps Rn onto, what we call onto Rm, if and only if the columns of A span Rm. This one should make the absolute most sense. If we have a linear transformation and we're calling it, 1, 2, 3, 4, whatever, right? And the idea is that if we're going from some space to another space, the literal definition of being onto is that every single output has an associated input. So in other words, we're starting off in our domain, we're starting off over here, and every single one of these guys that lives over here, every single possible little vector that lives over here has to have something from the domain, which means that we need to be able to span the codomain, right? That these column vectors here have to give us every single possible vector be in our codomain Rm. It almost makes too much sense. So we've now learned our first kind of use for span, which is that if the vectors span our codomain space, we have successfully created an onto transformation at the very least. And don't worry, we're going to do an actual example to kind of drive all this home. But the second criteria, or the second thing that happens here, is that T is 1 to 1, if and only if, and we shorthand that in mathematics by writing two F's. If and only if, that's the same thing as writing this. Basically, if one is true, then the other is true, and if one is false, then the other is false as well. So T is 1 to 1 if and only if the columns of A are linearly what? Independent. So why does this second one make sense? It's not too hard to think about, right? So the idea is kind of in short, without going into too much detail. If I have like some vectors, right? So let's say I have the vector 1, 2, 3, 4, 5, 6. These are clearly linearly independent. And I think about the span of these two vectors, right? So this is a 3 by 2 matrix, meaning that we would take in some 2 by 1 vector, and we're mapping to, in this case, R3. So this has to be a 3 by 1 solution. And so since we're going to R3, if we were to talk about the span of the two vectors that are in our matrix A right here, right? If we're talking about the span of the two vectors in this matrix right here, these vectors, right, even though there's two of them and they're 3D, they can at most span just a plane at best, right? Because they're linearly independent. They are two vectors that look like this, and the span of them will, ad infinitum, kind of go off in every direction and create a plane of values, which is kind of what we call a subset of R3. But the idea is that, this matrix, if we consider the span, will be able to give us a bunch of vectors in R3. It's going to give us a bunch. You put in any vector here you want from R2, it's going to give us a vector in R3. The problem is it's not going to give us all of R3, but it will guarantee us the 1-to-1 bit. So that's, without going too kind of in depth, the idea is that looking at both of these statements, you can figure out whether or not you have one-to-one or onto depending on the matrix. So again, we get onto if these columns were to span the entire space. So down here, this is an example of a matrix that is, represents a transformation that is not onto, because we only have 2 vectors there, but we're going to 3D space, so it's impossible to span all of R3. So we don't get that, but we do get one-to-one because, pictorially what's happening here is that there's some x1 vectors here, x2 vectors that are in our domain, etc. And there's some b1 vectors here and some b2 vectors here and some b3 vectors here. And what's happening is that even though we're not able to cover all of the vectors in R3, right? There's too many of them. These vectors here can only span, and all their linear combinations would only ever be able to give us so many of the ones in R3, but this is still a one-to-one relationship. So naturally, I would say, after all the theory, I think theory tends to kind of hurt people's brains, and that's not entirely my intention in this class. So I think we should just do one quick example, which is, so let's let T be a transformation, be a linear transformation, such that T of, we'll say, some input vector x1, x2 is equal to some output vector that looks like this. So 3x1 plus x2, 5x1 plus 7x2, and x1 plus 3x2. And 2 questions that we're going to get is the transformation T one-to-one? Is it one-to-one? And is T onto? Okay, so first and foremost, it's a good idea to rewrite this thing here on the left side in the form of a matrix. So 3, 5, 1, and then 1, 7, 3. And then we have, our input vector here is an input vector x1, x2. And so what do we expect to get out? Well, again, this is a 3 by 2, this is a 2 by 1. So we should expect to get out some 3 by 1 matrix. And just by looking at this, we know that, this transformation T is going to be going from a domain of R2, and we're mapping over to R3. And we're trying to ask the question, are we one-to-one and are we onto? So if we scroll back up to our conditions here, okay, we are onto if and only if the columns of A span Rm. So in our case, we have 2 columns, right? We have 2 columns, which means we have 2 kind of column vectors. And these column vectors, no matter how many different combinations we make of them, right? Because another way of thinking about this is x1 times 3, 5, 1 plus x2 times 1, 7, 3. This is going to equal some vector b that's in R3, but no matter how hard we try, we're not going to be able to get all of R3. It's not possible because we only have 2 vectors. At most, this is going to be a plane of values. So this is not onto, we fail the onto test. How do we check for linear independence? So if we had more than 2 vectors, we would need to RREF this thing, but we can kind of clearly see that because, if I were to multiply to check to see if one of these vectors is linearly dependent on the other, you're only looking to see if it's a multiple of the other one. But clearly, to get from the first vector to the second vector, I'd have to multiply by 3, but I don't multiply by 3 for all of these because clearly they don't match up. So these vectors here are definitely linearly independent. These column vectors are linearly independent, and so therefore we immediately get that this is a one-to-one transformation. So we fail the onto, we get one-to-one. We could make this both a one-to-one and onto transformation if we wanted to, by keeping 3, 5, 1, 1, 7, 3, and we could add a third vector. Now what is it? No idea. But we could add a third vector, and as long as this third vector is linearly independent, or rather all 3 of these vectors are linearly independent at the same time, then the span of these three vectors would give us all of R3. And on top of that, we would have three linearly independent vectors. And so we would have 1 to 1 and onto at the same time. So the more you do the homework, the more you're going to notice. Sometimes your matrices are really big. Sometimes they're really long. Maybe there's 7 rows and 5 columns or stuff like that. And you're going to start noticing some patterns about what kind of matrices you really need to have in order to have a chance of being 1 to 1 or onto and things like that. So that's going to do it for this video. I think we kind of beat the dead horse, so to speak, of covering, what does it mean to be 1 to 1? What does it mean onto? Why are we interested in classifying these? And we'll pick up with a little bit more theory next week.